My dear students, today's topic is Kirchoff Laws. Here, Kirchoff extended the Ohm's law to the complicated circuits to enable to determine the current in any part of the circuit by using two laws. And those laws are called as the Kirchoff laws. In that, the first law, it states that the algebraic sum of the currents at a junction is zero, or the sum of the currents entering the junction is equal to the sum of the currents leaving the junction. That is, it states that the algebraic sum of currents at a junction is zero, or sum of the currents entering the junction is equal to sum of currents leaving the junction. Sum of currents entering the junction is equal to sum of the currents leaving the junction. That is, it is also called as Kirchoff current law. Simply, it is KCL. It is also called as Kirchoff's current law, and it is a direct consequence of law of conservation of charges. It is a direct consequence of law of conservation of charges. This is the first law. That means, suppose if you consider there is this a sign convention. For this we have to use the sign convention as first one, currents entering the junction are taken as positive. Currents entering the junction are taken as positive. Second one, currents leaving the junction are taken as negative. This is the thing. Suppose if this is a junction J and the currents are entering and leaving at different parts, can give like this. Suppose this is I1, this is the junction J, and it's I1, I2, I3, I4 and I5. Suppose you are given. Here, towards this junction, I1, I3, I5 are entering, I2 and I4 are leaving. So currents entering the junction are taken as positive. So I1 positive, current leaving the junction negative, current again positive, negative and positive like this. So the algebraic sum of the currents at a junction is zero. Or otherwise, you can take that I1 plus I3 plus I5 is equals to I2 plus I4, which implies that these are the currents entering the junction is equal to currents leaving the junction. Currents entering the junction is equal to currents leaving the junction. This is the Kirchoff's first law. Now, second law. It states that the algebraic sum of potential differences in a closed mesh or loop is zero. Algebraic sum of potential differences in a closed mesh or loop is zero. Or otherwise, we can say that the sum of the products of current and resistance, sum of the products of current and resistance in a closed loop is equal to the sum of the EMFs in the closed loop. That's another one. The sum of the products of the current and resistances in a closed mesh or loop is equal to the sum of the EMFs in the closed loop. And here, this is also called as Kirchoff voltage law. Kirchoff voltage law. Within brackets, we can say that KVL. And very important thing, it is a direct consequence law of conservation of energy. This is called as Kirchoff's voltage law. It is a direct consequence of law of conservation of energy. And now, sign convention for this. First point is in the direction of flow of current, in the direction of flow of current, the product of current and resistance should be taken as negative. The product of current and resistance should be taken as negative, because suppose if you consider this is the flow of current in this direction, and if R is the resistance you have taken, current always flows from the body at higher potential to the lower potential. Suppose this is a plus, you can take this minus. So current is flowing from higher potential to lower potential. So in the direction of flow of current, the potential difference should be taken as negative. That is, V is negative. Then second one, opposite to the direction of flow of current the product of current and resistance should be taken as negative, should be taken as positive. If you measure the potential difference opposite to this is A and this is B, and you are measuring from A to B, then here if you take this VAB is negative, here VAB is positive. This is the sign convention regarding the potential difference. And third one, in case of a cell, if the current flows from negative terminal to positive terminal, then the EMF should be taken as positive. The EMF should be taken as positive. Suppose this is the, and the current is flowing, this is minus and this is plus, then the EMF is always be taken as positive. That is here, that small e is positive. Fourth one, if the current flows from positive terminal to the negative terminal, then the EMF should be taken as negative. If this is the case, and here this is plus and this is minus, so A is negative. This is the sign convention that we have to adopt while solving the problems related with Kirchoff laws. And here, if you apply all these things for any given, suppose you are given a loop like this. Now, you can consider this is A, B, C, D, E, F, G, H. Like that you have taken. And this is having an EMF E1, this is having an EMF E2, this is having an EMF E3. And let us say this is R1, this is R2, this is R3. Then, if I is the current that is flowing through this, if R is the internal resistance of the cell also, if you have taken, at this junction, let us see if I1 is the current flowing through this, and I minus I1 is the current flowing through this part of the circuit. Then, if you observe this, we have a loop A, B, C, D, E, F, A is one closed loop. A, B, G, H, A is another closed loop. Or A, H, G, B, C, D, E, F, A like that, other closed loop. So there are so many loops we have. In that case, if you apply KVL, that is Kirchoff voltage law, the second law, to the loop A, B, C, D, E, F, A. When you apply this loop to this one, A to B, in the direction of flow of current, then it is given by plus E1, like this only. Then here C to D, in the direction of flow of current, this will be given as minus I1 R1, and here also minus I2 R2, and here minus to plus. So plus E3 minus I1 R2, I1 R3 minus I into small r, this must be equal to 0, because here in this internal resistance is given. Therefore, if you can observe this, E1 plus E3 is equals to I1 R1 plus I2 R2 plus I1 R3 plus IR. So, it is clear that the algebraic sum of the currents, algebraic sum of the products of the currents and the resistance in a closed mesh is equal to the total EMF in the circuit. And also we can apply KVL to the loop ABGHA. For this loop, if you can see that minus I minus I1 into, if you have a resistance of R4 for this and R4, here the current is flowing in this direction, positive to negative, so minus E2 and then minus IR plus E1 is equals to 0. Therefore, it is given by E1 minus E2 is equals to IR plus I minus I1 into R4. Like that, for any given complex circuit, you can easily solve the problems based on this Kirchoff laws. Then there are two applications of this Kirchoff laws. First one is Wheatstone bridge, and the second one is meter bridge. Applications of Kirchoff laws. In that, first one is Wheatstone bridge. This Wheatstone bridge is basically used to determine the unknown resistance of a given conductor, or to compare the resistances of the given two conductors. The basic construction of this Wheatstone bridge is, it consists of four conductors of resistances P, Q, R and S. Are joined like this. The arrangement of the Wheatstone bridge is four conductors of resistances P, Q, R, S are joined to form a quadrilateral. Are joined to form like this. And now, this is the terminals A, B, C and D. Now the terminals A and C are connected to a cell of EMF capital E, and the terminals B and D are connected to a galvanometer of resistance capital. This arrangement is called as Wheatstone bridge. So once again, four conductors P, Q, R, S are joined to form a quadrilateral A, B, C, D. The terminals A and C are connected to a cell of EMF capital E. The terminals B and D are connected to a galvanometer of resistance capital G. Now, if I is the current flowing through this, While reaching the junction A, it splits up as I1 and I2. At the junction B, the current is divided as IG and I3. The current IG and I2 combines at junction D and flows through S as I4. Again, this I3 and I4 combines and flows to the external circle as I. Now, what is the expression for the balancing condition of Wheatstone bridge? To arrive that one, we had to apply KCL as well as KVL. That is Kirchoff's current law and Kirchoff's voltage law. So, applying KCL to the junction B. If you apply KCL to the junction, which currents are entering? I1 is only entering at junction B. Which currents are leaving? I3 and IG. Then it is given by I1 is equals to I3 plus IG. That is the first equation. Again, apply KCL, that is Kirchoff current law, to the junction D. When you apply this to the junction D, which currents are entering? I2 is entering, IG is entering, and these two are combined and flows through as I4. Therefore, you can say that I2 plus IG is equals to I4 is the second equation. Now, if you observe this diagram, ABDE one closed loop, BCDB one closed loop, ABCEA or ADCEA, there are so many loops are available. The simplest loops when you are taken for applying KVL, that is Kirchoff's voltage law, which is nothing but second law, to the loop ABDA. If you apply this to the loop ABDA, then what happens? In the direction of flow of current, A to B the current is flowing. So it is minus I1P. In the direction of flow, minus IgG, and it's moving opposite the direction of flow. Minus means plus. I2R is equal to 0. This is equation number 3. And apply KVL to the loop BC. In the direction of flow current, product of current and resistance should be taken as negative. Here opposite the direction of flow of current, so plus I4, yes, plus IgG is equal to 0 is the equation. Now, if the Wheatstone bridge is balanced, the current through galvanometer becomes 0. So, the resistances are so adjusted until the deflection in the galvanometer becomes 0. The resistance are so adjusted until the deflection in the galvanometer becomes 0. Then the bridge is said to be balanced. And once you got the idea of this, once the bridge is said to be balanced, then from equation 3, a balancing condition, Ig is equals to 0. Therefore, from equation 3, minus I1P plus I2R is equal to 0, which implies I1P is equals to I2R. That is equation number 5. Similarly, from equation 4 minus I3Q plus I4S is equal to 0. Therefore, I3Q is equal to I4S is equation number 6. Therefore, 5 divided by 6, I1P by I3Q is equal to I2R by I4S. But from equation 1 and 2, that is equation number 7. Therefore, now from equation 1, I1 is equals to I3. And from equation 2, I2 is equals to I4. Thereby, I1P by I1Q is equals to I2R by I2S. Therefore, P by Q is equals to R by S. This is the balancing condition of Wheatstone bridge. This is the balanced condition of Wheatstone bridge. Now, in that condition, if you consider this, this is a P, Q, R and S. Then the equivalent resistance between A and C. Here, when no current flows through the galvanometer, the central part of the circuit can be removed. Thereby, the equivalent resistance between A and C is RAC is equals to P plus Q into R plus S by P plus Q plus R plus S. Because these two are in series and these two are in series and these two are in parallel, then we can apply the formula R1 R2 by R1 plus R2 in parallel connection. This is the one application related to the Wheatstone bridge, Kirchoff Laws. So, this is very important. What is the balance condition of Wheatstone bridge means? It is P by Q is equals to R by S. And another application is meter bridge. The second one is meter bridge. This meter bridge means it is simply nothing but it is also works under the balancing condition of Wheatstone bridge. It is used to determine the unknown resistance of a given conductor, to determine the specific resistance of a given conductor, and also to compare the ratio of the resistances. In that, it's very simple. Only thing, this meter bridge will mainly consist of a manganese wire of length 1 meter. Manganese wire of length 1 meter. It is mounted on a graduated wooden board like this. This is A and this is B, having a length of this. Now, it is connected like this. This is the, it consists of two L-shaped rectangular metal strips mounted on a graduated wooden pole. The terminals can be connected to a manganese wire of length 1 meter. Now, a cell of known EMF capital E, apply K, and the rheostat RH are connected like this. And now a known cell a wire of unknown resistance connected in this. First I will give the diagram. Resistance box. This is a simple circuit that we are going to provide for the, this is a unknown resistance in the first thing is, this mainly consists of manganese wire of length 1 meter. It is mounted on a graduated wooden board. Graduated means you have to provide with a meter scale to measure the balancing ones. Two L-shaped metal strips are mounted on the graduated wooden board. The terminals M and N are connected to a cell of EMF E and plug K as shown. And a metal strip C is mounted in between these two, so that it provides two gaps. In the left gap, a wire of unknown resistance X is connected. In the right gap, a known resistance box having a fixed resistance is connected. The central part of the metal strip C is connected to a high resistance box, a galvanometer jockey, a galvanometer of resistance capital J and jockey J are connected like this. Now whenever the jockey J is present at the terminals A and B, if you get opposite deflection, then the connections are said to be correct. Now, a known resistance is kept in the resistance box and the jockey J slowly moved from left to right. At one instant, the galvanometer gives 0 deflection. That means the meter bridge is said to be balanced. Then the distance from A to J is called as the balancing length. This we can also write at the balancing condition of this Whitson bridge. We can also connect like this. This is A. You can take this is X and this is C, and now this is RB that is having a resistance R like this. This is L1, this is L2, and this is HR and galvanometer G, and this is jockey J. This L1 is given as L, L2 is given as 100 minus L. Whenever the current through the galvanometer becomes 0, this part can be eliminated. So the bridge is said to be balanced. Under the balancing condition of Whitson bridge, then X by R should be equals to L1 by L2, or X by R is equal to L by 100 minus L. So only a simple formula based question. And specific resistance rho is equal to XA by L, or X into pi R square by L, ohms centimeters. This is another application of the